Okay, so first we're going to talk about the aerobic pathway of respiration here. And so this is going to use oxygen. So this is us breathing. Aerobic means breathing here. So it's going to rely on oxygen and generating CO2. So, and you're going to be like, how do you do that otherwise? That's what we'll talk about in the next video. So overall, we have our reaction. We're just going to focus on glucose here. So we got our chemical equation. So we got C6H12O6 plus 6 oxygens. I'm going to do my arrow down here because I need some... Oh, actually I can go underneath. We'll do that. It gives us 6 CO2 and 6 H2O. And you've seen this equation a number of times now, and you've probably seen it with plus some number of kilojoules of energy. But now we're going to say, well, we start out with about 34 ADP. They swoop in, and we get about 34 ATP. And I say about, you think, well, how do you get an about? Well, we're going to talk about that. It's a little tricky. So, there's 4 steps that we're going to discuss. Well, I mean, there just are 4 steps, so we're going to discuss all 4. It makes it sound like I was leaving one out. Like, well, there's actually 7, but we're not now. It's 4 steps. When you go very macro, you really zoom out like we did. Like when you zoom in on that last video, on that big poster, you zoom in. Yeah, there's a lot of steps, but when you zoom out, there's like 4 major pieces. That's what we're going to talk about. So step 1 is glycolysis. Okay, so what are we glossing over in glycolysis? Well, it's 10 reactions. Biochemistry is actually really complicated, if you didn't know that. If I haven't made that clear already, or if you just never would have assumed. Who would have ever guessed, right? Biochemistry, it's difficult. So there's 10 reactions. We're not going to show a single reaction. We're going to show the result, the overall net of those 10 reactions. But I want you to understand that I'm being very kind here. So you have your glucose, and you're going to have 2 ADP. So we're also going to have 2 NAD+. And we're going to come out of this with what we call 2 pyruvates and 2 ATP. So we're actually making some ATP right off the bat, which is nice. Not a lot, only 2. Remember, overall we're getting like 34. So this isn't much compared to the total, but it's a great start. Like, we get some right off the bat. And then we get 2 NADH/H pluses. These are going to be really important later. We're going to talk about those. This is actually secretly what we're making in these early steps, like step 1 and 2 and 3. We're making a bunch of these and FADH2s. But for now, we're going to keep our eye on the carbons. What are the carbons doing? Well, we have our glucose. It's a 6-member ring, and we break it in half, and it's 2 3-carbon chains. We go from 1 6-carbon molecule to 2 3-carbon molecules. Because remember, we're going to have to break all of these carbon-carbon bonds, because ultimately they're going to get turned into carbon dioxide, and there's only 1 carbon in that. It's not 2 carbons, right? It's just 1. So it's going to get turned into carbon dioxide. Every single carbon is going to get broken off from each other completely, and that's the energy we're storing in things like ATP or this guy right here, NADH. So this step occurs in the cytoplasm. That's kind of the last detail here. And that gets us started. And again, we're just focusing on glucose. There's different pathways, as I showed earlier, for different biomolecules that you can burn for energy. So amino acids, nucleic acids, lipids, they have different pathways. So we are looking at just the carbohydrate pathway and just the one for glucose. Fructose is going to be a little bit different. And we're not going to worry about that. Okay, so this feeds us into step 2. So those carbons, we're just kind of think of it as like a chain of custody on the carbons. So in step 2, all of our carbon is now tied up in the form of being a molecule called pyruvate, which is 3 carbons long. And so that's what we start with. And this step, the name of this step, by the way, totally gives away what it does. This is the most uncreatively named step of all time. This step is called formation. And by the way, that says a lot, right? Because we've had some very non-creative names in this class. But this one I think really takes the cake. Formation of acetyl-CoA. You'll never guess what we do in this step. You don't even know what acetyl-CoA is, but you know we're making it. We didn't start with it, right? We're starting with pyruvate. So we have our 2-pyruvate from earlier. Okay. And so this is where our carbon is. Again, we took a sugar and we just basically broke it in half. We made pyruvate. If you want to know what pyruvate looks like, yeah, just look it up. That's not really what we're doing here. We're also going to have 2 coenzyme A's. It might seem like maybe where that comes from. And we're going to have a couple more NAD pluses. Which, by the way, if you're seeing NAD plus involved, what does that mean is happening? What's happening in these reactions? We're having a redox reaction if you have NAD plus. And you can probably guess what type of redox reaction that's occurring if you remember what NAD plus is used for versus FADH. So, either, and are we oxidizing or reducing if we're starting with this guy? These are all things that you can think about here. And so there's going to be some oxidoreductase involved in here, some type of oxidoreductase. So we take our 2 pyruvates, our coenzyme A, and we're actually going to turn it into acetyl-CoA, and this is often called the carbon currency of the cell. This is kind of where a lot of those other pathways link in. There's different ways of making acetyl-CoA. What we're talking about is how we make it out of a carbohydrate, specifically glucose. But when you break down a fatty acid, it's going to be turned into acetyl-CoA. That's why it's called the carbon currency, because ultimately we're making CO2 and ATP. We need carbons to do that. We have different sources, but it feeds in, there's different ways, it's like little contributing streams turn into a big river. That's what's happening. So, and this is where they meet, acetyl-CoA for the most part. And so it's a 2-carbon molecule. And so we take our 2 pyruvates and we get 2 acetyl-CoAs. Now, this only accounts for 4 carbons. Where'd the other 2 go? Because this is 6 right here. This is 2 times 3. Now we have 2 times 2. So we had 6. Now we have 4. Well, that means we have 2 CO2s already. Which, hey, we're increasing the number of carbon-oxygen bonds here. Well, that might be why we have some NAD pluses involved. And what happens to those? Well, they just become NADH and H pluses. Alright, now here's the cool thing. This is one reaction. So that's not so bad. And it is going to occur in the mitochondria. So only the first step occurs in the cytoplasm. Everything after that, mitochondria. So now we are in the powerhouse of the cell. This thing is built to do this. It is built to make ATP. And I'm going to talk more about the mitochondria with the electron transport chain, because that's where you really see how the function that it performs is so completely tied to its form, its shape, how it's built. And also I'll talk about how we ended up with mitochondria, because cells didn't always have them. Cells didn't always have them. Eukaryotic cells, it's a special kind of organelle. We're going to talk about that. Okay, so where have our carbons ended up? We're not going to, once they're CO2, they're done. All right, that's that's like you get the penny at the cash register. You take a penny, leave a penny. You're just like, I don't want to deal with it. I don't even have a coin pouch in my wallet anymore because inflation. What's the point? And then if I do have any actual, like if I have quarters or whatever, you have a change thing at home, you just throw them in. Because, one day you're going to go to a coin star, but you never do. You just keep getting a bigger and bigger change thing. Until one day you have to do, like, laundry at a laundromat, and you have to fish out all the quarters. Anyway, like, one person can relate to that out there. Like, they had their washer go down or whatever. Or, you're in an apartment complex. I've been there. My advice is never use the complex's washers. Just go to a laundromat. Find a nice laundromat. Don't go to, like, a bad one. Last time I went to use a laundromat, I was renting a place that had its own washer and dryer, and that already like half of you don't care. But this is a good story because my washer broke, or no, it was shared between me and another unit, and it was actually owned by the other tenants, and they moved out and they took them. And my landlord didn't tell me, so I went to do laundry, and it was just like an empty laundry room. That's what happened. That's right. And I called him, and I was like, "Hey, man, I think they stole your washer and dryer." And he went, "Oh, did they take those?" I was like, "Yeah." He's like, "Oh, I thought they just were gonna leave them for the place." I was like, "Oh no, that was their washer and dryer. So they didn't steal your washer and dryer. You're just hoping that they wouldn't move them," which surprised they did. So luckily I live down the street from a laundromat, and so I go to the laundromat, and it had just caught on fire. Like that, the fire department was there. They were putting out. They cut a big hole in the roof to let all the smoke out. I guess some homeless people showed up, and it rained, and they threw their clothes just straight in the dryer, and that caught the place on fire or something. I don't know. But I mean, I guess it could have been worse. I could have been in there with my stuff, all my clothes, when it did catch on fire. That would have been rough. But still, it was just like there's just me standing there. I walk a block. Like I had a plan. I had a backup plan, and it all fell apart. Okay, so good thing no one ever complains about my stories that I tell in my evaluations or anything. Step 3. So we're going to take our acetyl-CoA, and this is where, other things are going to feed in at this point, potentially. If you look at that big poster, and I will put that on the Moodle page in the, wherever, I forget the exact name, what is it? There's like a folder I can put it in. Or additional resources. I'll put it in additional resources. So I've already got the scaled down one there. I'll make sure to add the really complicated one, and then you can impress people and be like, look what I learned, but really just, don't show them the scaled down version that we're really going to talk about, which I'm breaking down here, by the way. So you can see that all the other stuff feeds into acetyl-CoA. Where's this acetyl-CoA go? So there's all these different ways of generating acetyl-CoA, and this is going to go into the citric acid cycle, sometimes called the Krebs cycle, and that is step 3. Now, oh yeah, let me get the name on here. Citric acid cycle. Okay. And this is 8 reactions. And it is a cycle. That's why it's always drawn as a circle. It feeds around and around and around. So there's different contributors and stuff. It can be pretty complicated. And everything, by the way, from step 2 on is going to occur in the mitochondria. I'll remind you of that step by step. But we're going to definitely start with our 2-acetyl-CoA, right? Because we're just tracking the carbon. We're just following the carbon. It's like you're the IRS. You follow the money. Unless there's too much of it, and then you can't do your job or whatever. Like, I have to pay my taxes. I don't make enough money to not pay my taxes. That's the joke I always tell. If you make enough, apparently you don't have to. So, we're going to make a little bit more ATP here, which means we're going to have to start with some ADP. Excuse me. Good thing T and D don't sound anything alike. But we're also going to have 6 NAD pluses. That's quite a bit. And we're going to have 2 FADs. Alright. So that's all the stuff we're starting with here. And I'm really distilling down this cycle. You can read more about it if you want. I'm not going to make you memorize it or anything. But just understand that there's a process. These carbons are being pushed through piece by piece. These things are being mediated. And so you see the NAD+, you see the FAD, you're like, oh, there's going to be some oxidoreductases here. We're going to change the number of, carbon bonds. We're going to change, double bonds. We're going to change out some carbon-oxygen bonds. We are going to oxidize. And so when we are done with this step, all of our carbon is going to be CO2. So we have 4 carbons remaining of the 6 we started with. And those are going to be CO2s. So we are done with the carbons. There's still a step left. So think about what we've been making along the way. It's like the real journey was the friends you made along the way. It turns out it wasn't about the CO2 necessarily. We're going to get our 2 ATP. We are going to have all these NADs pluses become NADHs. Oops, there's a D in there, I swear. / H pluses. And we're going to have 2 FADH2s. Alright, so this occurs in the mitochondria. And it starts with the acetyl-CoA. And remember, that's where other processes tend to feed in, so with that acetyl-CoA. This is in the mitochondria. The mitochondria is built to do this. This is in the heart of the mitochondria. All the way in the middle of the middle, you know? And so the last step is the step that the mitochondria was built to do, okay? So, step 4. Now keep in mind, we are done with the carbon. Alright? So what do we have left to work with? Well, all of those NADHs, all those FADH2s, those have stored energy. Those are actually secretly what they're really holding on to are electrons, energized electrons. And we're gonna just sneak the energy out piece by piece out of those electrons and then use it to make ATP. And it really is, like, the mitochondria is a factory that is what it's really built to do, is turn NADH and FADH2 into energy that gets turned into ATP. And again, that's why I really encourage you to watch that animated video of the electron transport chain, because that's what we have here. But I'm going to call it oxidative, there it is, phosphorylation, which is like, you know, it's a pretty cool name for like a metal band or something, I think, you know, open for Metallica, like opening act, oxidative phosphorylation. Could sell some cool t-shirts out of it. Alright, so this is complicated. I'm not even going to say, like, this isn't really chemical reactions anymore. It is like a physical process. Almost. Like, there is chemistry involved. And I'm just going to remind you, it's the electron transport chain. So this isn't like A plus B becomes C. This is far more intricate. And I struggle to describe it verbally because it really helps to have visuals. And I'm going to have a whole video that I do on this next. But I will say that this is where we make the majority of the ATP. Because keep in mind, we've only made 4, and we make about 34. And one of the reasons I say about 34 is the conversion of NADH and FADH2 to ATP. It's not a direct chemical reaction. It's not this like 1-to-1 or 1-to-2 process. It gets a little fuzzy in the numbers, so we put about 34. Okay, so we've made 4 already, so I'm going to say we have 30 more ADP. We've made 4 ATP. And we're going to have, you know, we need 30 phosphates for that, so inorganic phosphates, PI. We're going to have some O2. Keep in mind, you haven't seen any O2 show up yet, really, right? Like, where's that oxygen been coming from? Well, the answer is we've actually been stealing oxygen off of water at every step of the way so far. When we were making CO2 before, we're actually using water to do it. But now, what's the other product of a combustion reaction, right? We haven't made any water. We've only made the CO2. So now we've got to make the waters. Because, you know, we're going to get 6 CO2 and 6 waters out of every glucose. We've got the 6 CO2. We haven't got any of the waters. Okay, so what are we going to do next? Well, now we're going to pile in all of that NADH. And FADH2 that we've generated. This is the overall reaction, And so what do we get? Well, we're going to use these guys with this to make water and a whole bunch of ATP. So all these ADPs get turned into ATP. And so this is the step where we really make ATP. And this is always happening, by the way. Whether we're awake or we're asleep, we're generating ATP as long as we're alive. The second we stop generating ATP, well, about 30 seconds after we stop generating ATP, we're dead. And that's if you're in like really conservative, you know, most people it's probably like 15 to 20 seconds. So that's something that's happening. It's happening right now when I'm making this video. It's happening for you right now while you're watching the video. You are making this ATP. This process is happening. You are almost certainly not running a sprint while you watch this video. So you are in aerobic respiration. You are doing this. So we're also going to get 8 waters. We're going to get all of our NAD pluses back. And guess what we can do with these? Well, we can just send them back to the earlier steps. They can be used in glycolysis or the citric acid cycle, or formation of acetyl-CoA. And we get our FAD back as well. And this is not just in the mitochondria, this is totally because of the mitochondria. And so this is aerobic. We are using oxygen. We are generating a bunch of ATP, and we're doing it very efficiently. We get about 34 ATP out of a single glucose molecule. And so this is the aerobic pathway, and aerobic means it uses air, uses oxygen. And this is what we talked about. So it does it in 4 steps. And we talked about all the steps, what they do. But keep in mind, this is the big picture, and this is aerobic respiration. Now, the next video we're going to talk about anaerobic respiration, and it's a much simpler process overall. So I'll spend that video, I'll have time in that video where I talk about the difference between the two as well, and like when you would switch over. But for now, just make sure that the idea of aerobic respiration makes sense. This is our end goal. We're making a bunch of ATP. We are using the mitochondria to do it. It does it very efficiently. It's not necessarily fast because there's so many steps involved. And when we make that ATP, it's in the middle of the mitochondria. It has to make its way completely out of the mitochondria and go where it's needed. It gets used up, turned into ADP. It's got to return. And so there's shipping time involved. It's not manufactured on site. It's made somewhere else, and it's got to ship out of the mitochondria to where it's needed. And it's not like it's directly transported either. Everything in the cell is kind of random motion, so it just sort of floats out and goes somewhere until it's needed, and then eventually it floats out and it comes back. So it's all driven by what we call diffusion, which is just stuff floating around it in water. So you see a bunch of people on floaties in a pool, they're diffusing around. They're not. You're on a boat, you control. You have propeller. You're choosing where you go. You're making decisions. You're choosing a direction. When you're on a little floaty, you just sort of go wherever. Or a life raft, right? You just sort of go with the flow, and that's what happens in the cell with this ATP that's generated. So it's efficient, but not fast, and that'll be a key thing for the next video. So this is the aerobic pathway. We're going to talk about the anaerobic pathway next.